If the acceleration is 0, the velocity is constant because acceleration is delta v over delta t. And if that equals 0, then the change in velocity is 0. If acceleration is 0, then the change in velocity is 0. So the velocity is constant. And if it's stationary, the velocity is 0. And when we look at the forces, whatever they might be, say force 1 and force 2, they are equal and opposite to each other. For example, plus 8 and minus 8. The sum of the forces is the plus 8 minus 8, and therefore the sum of the forces is 0. So sum of the forces equals ma equals 0. An example of this might be a tug of war between two equal persons. A person standing on this side pulling with an 8 Newton force and a person standing on that side pulling with an 8 Newton force. The two remain stationary even though there are forces. So what this goes to show us also is that forces, just because they're forces, does not mean that there is motion. Forces can be balanced, and there isn't any motion at all. Now, I introduced this term, what we call a free body diagram, and there's two essential elements of a free body diagram, and this is an example of a free body diagram. It's pretty intuitive to understand. The first element to it is we take the object in question, an object, let's suppose this in this tug of war, it was actually tied onto a box. Let's say it was a box. The ropes were tied to a box, and they're pulling on the box. Well, the body involved is represented as a point mass at the center of mass. So that what we had there previously as a box represented as a point mass. Now, I drew it pretty large in this diagram so you could see it, but there could be some object there of any size like this, but this is just located at the center of mass. The second one, the force is represented as pulls on the body. So notice there's never an arrow pointing at the dot. They're all pulling out of it. This is a pull, and this is a pull, pulling on the body. And that's the way we visualize forces. We take the body that's being acted on, draw it as a dot, draw all the forces in the correct geometry to length, to scale, to help figure out what's going on. And since we've drawn them equal length that are opposite to each other, they're balanced and add up to 0. Now let's talk about translational equilibrium. Translational means translating or moving down an axis at constant velocity. So translation means moving down an axis. Equilibrium means balanced forces. And that then means that the velocity is constant. So we have a sum of the forces equals ma equals 0. Therefore, the acceleration is 0. But notice in this case, we have a constant velocity that we're talking about. It's moving down an axis. A constant velocity that's not 0. Let's say it's plus 6 meters per second or minus 7 meters per second. It has a velocity and it remains constant. Well, if the velocity remains constant, the change in velocity is 0. And if the change in velocity is 0, the acceleration is 0. If the acceleration is 0, then the sum of the forces is 0. And so there's a logical train that goes forward and backward. If the sum of the forces is 0, then the acceleration must be 0. The opposite is true. If the acceleration is 0, then the sum of the forces must be 0. So here we have like a case here. Let's say this is plus 12 newtons and this is minus 12 newtons. And we have a tug of war going on. But what I forgot to tell you is this is all on a railway car moving down a railway track at 20 meters per second. So the velocity equals 0 from the reference frame of where the people are standing, but the whole system itself, the entire system is moving down an axis at constant velocity. That's what translational equilibrium is. So another example might be that it's rotating on the Earth. We tend to think of ourselves as being stationary, but in reality, we are situated on the Earth and we are rotating, at over 1,000 miles per hour. That's about like 1,400 kilometers per hour. So we're moving at an incredibly fast clip. We're not even aware of it. We're in translational equilibrium. Or the Earth moving through space. The Earth itself is translating along this line that represents the orbit as it revolves around the sun, and I believe that's about 66,000 miles per second, something like that. An ungodly, imaginably fast speed that we're moving through space, and we're completely unaware of it. So if you look at these two free body diagrams, they look identical to each other. Equal and balanced. So when you look at these free body diagrams, the only thing you can say about them is that the forces are balanced and that the accelerations are zero. So that leads us to this final point, which is in terms of forces, there's no difference between an object at rest and one moving at constant velocity. And that is one of the most difficult things that we have, that we can overcome when we are first learning physics. Is that in terms of forces, there's no difference between constant velocity of 0 and a constant velocity of, say, 9 meters per second. Our last state is disequilibrium, or not being in equilibrium. So here we have the sum of the forces is not 0, so therefore the acceleration is not 0. It's a number like +2 or -6 meters per second squared. The velocity is changing, and therefore it's not equal to 0 for most of the time. And what this might look like in our free body diagram is we have a 20 Newton force in this direction and a 12 Newton force in that direction. And when you add these up, you get a net force of +8. The sum of the forces is 20 plus -12, which is 8 newtons. And that, of course, is the sum of the forces is the net force. So we get a net force of 8 newtons. Now let's suppose we do a calculation here, and this is the standard way, by the way, we use Newton's second law. We start out by saying F net is the sum of the forces. The net force is ma, and our forces are 20 and -12, and ma then is 8. The net force is 8. And so if the mass happens to be 4, then the acceleration is 8 divided by the m, or 2 meters per second squared.